In this video, we're going to expand upon our knowledge of pH buffers and look at more complicated calculations involving buffer solutions. In the previous video, we only looked at buffer solutions at the transition point where the concentration of acid and conjugate base were equal, but as we'll see in this video, this is not necessarily always true. In fact, we can see it in this region of the graph where we graph the pH of an acidic buffer solution versus the volume of base that we add in order to increase the pH. Again, not surprisingly, the more base we add, the more the pH increases, but we can see that the pH remains relatively constant around this region here and not simply at the transition point, which is why we call this region here the buffer region. Now, the reason why the buffer region exists is because we have a fairly large amount of acid and conjugate base that make up our buffer solution, so that as long as we have enough of each of these, we can neutralize any OH- or H3O+ that is added to the solution and keep the pH around the buffer region relatively stable. Now, the reason why we would want a buffer solution that doesn't necessarily have the same pH as the transition point is relatively simple. The point of buffer solutions is to prevent pH change from being significant. For example, the human body is filled with many different buffer solutions that all keep the pH of the human body around 7. Why 7? Because 70 to 75% of the human body is made of water. However, under different conditions, the pH that we want to stabilize is not necessarily going to be 7. For example, in certain industrial chemical situations that involve highly concentrated acids or bases. In other words, depending on the pH that we want to keep stable, we can change the starting pH of the buffer solution by either increasing or decreasing the amount of acid and conjugate base that we have. So let's look at how we can calculate the pH of buffer solutions, starting with the simplest situation, buffers at the transition point. So because the transition point has an equal concentration of the acid and conjugate base forms, our Ka expression becomes much simpler than how it normally is. Now, because the concentration of our acid and conjugate base are equal, we can cancel them out, meaning that our Ka is simply equal to the concentration of H3O+. And if we know what our Ka expression is, which we do because we can look up the Ka of acetic acid on a data table, all we need to do is take the negative log of Ka, and that will give us the pH of our buffer solution as long as we are at the transition point. This comes, if you put all of this into your calculator correctly, the pH of a transition point buffer solution of acetic acid comes to approximately 4.7. However, again, this is not necessarily the pH of a buffer solution that we want to make. So how do we calculate the pH of a buffer solution where the concentration of acid and conjugate base are not equal? Well, we can do it in the same way, where instead of canceling our acid and conjugate base from the formula for Ka, we can just put these two numbers into the Ka expression itself, solve for the concentration of H3O+, and take the negative log of that in order to find the pH. If you were to do this, you'd get the correct answer. However, there is another way that we can streamline the Ka formula in order to make an equation that is a little bit more usable. So we know that pH is equal to the negative log of the concentration of hydronium, and since the concentration of hydronium is part of the Ka formula, we can modify it by taking the negative log of both sides of this expression. However, what do we do with this part of the equation here that actually lists the concentration of conjugate base and acid as a ratio? Well, if you remember your log rules and your log algebra from advanced functions, whenever we have a log of two numbers that are a product, we can separate them into a sum. So that means that the negative log of Ka is going to be equal to the negative log of the concentration of H3O plus, because again, we're separating these two terms that are a product of each other when we take the log into a sum, plus the negative log of the concentration of conjugate base divided by the concentration of acid. Now, we know that the negative log of Ka is going to be equal to the pKa, and we know that this term here, negative log of H3O+, is going to be equal to the pH, and whenever we add a negative number, that's the same thing as subtraction, so pH minus log of the concentration of A minus divided by the concentration of HA, and we can isolate pH by adding this term, the negative log of the ratio of acid and conjugate base, to the other side of the equation, where we would have pH is equal to pKa plus the log of the ratio between our conjugate base and acid. And again, through some fairly simple algebraic manipulation, we've changed the formula for Ka to look for pH rather than having to do two separate calculations where we find concentration of hydronium and then take the negative log of that. So this, again, is a different form of the Ka formula, which is what we call the Henderson-Hasselbach equation, named after the two chemists who devised it as an easy way to calculate the pH of buffer solutions. Now that we have this form, we can directly use this formula and put these concentrations directly into it. So the pH of our buffer solution is equal to the pKa, which is the negative log of Ka, 1.8 times 10 to the negative 5, plus the log of the ratio of the two concentrations. So our concentration of acetate is going to be 0.25, and the concentration of acetic acid is going to be 0.5. And if we put these numbers into our calculator, the pH of this buffer solution comes out to being around 4.4. Now, because we have more acid than we do base compared to the transition point, we would expect that our pH would be lower, because the more acid we have, the lower the pH is going to be. The final application of the Henderson-Hasselbach formula that we can use is, let's say that we know what the pH of a buffer solution is that we want to make, but we don't know exactly how much acid and conjugate base we need to mix together in order to get a buffer with a pH of 5.25 in this case. Well, again, we can just solve for a different variable. So we know that our pH is 5.25, which is equal to our pKa, which is negative log of the Ka of acetic acid, 1.8 times 10 to the negative 5, plus the log of the concentrations of our acid and conjugate base divided by each other. So in other words, all that we're doing is the same type of calculation, only this term here is our variable. So I'm going to simplify this so that we save a little bit of writing and say that this ratio of conjugate base to acid is going to be equal to x. So in other words, that means that the log of x is equal to 5.25 minus the negative log of our Ka value here. And then from here, we know that the opposite of log is 10 to the exponent 2. So if we wanted to algebraically write this out, we would say that x is equal to the inverse log, which is 10 to the exponent of 5.25 minus the negative log of our Ka value, 1.8 times 10 to the negative 5, and we've gotten to this point without using a calculator. So when you put this number into your calculator, you'll find that x, the ratio of the conjugate base and acid to each other, comes to approximately 3.20, or 3.2 with 2 significant digits. Now, because X is equal to the ratio of the concentration of acetate divided by the concentration of acetic acid, we can say, remember that every whole number is just a fraction of itself divided by 1, we can say that the concentration of acetate that is needed is approximately 3.2 moles per liter, while the concentration of acetic acid is simply 1 mole per liter, because 3.2 divided by 1 is going to be 3.2, which is the ratio we calculated using the Henderson-Hasselbach formula. So in this video, you should now have the knowledge to calculate how to find not just the pH of a buffer solution, but also to find what concentrations of weak acid and conjugate base you need to add together in order to get a buffer solution with a specific pH. And in the final video, we'll look at a few of the real-world applications of where our knowledge of buffer chemistry can be useful for understanding.